In this module, we will look at the flight control system of the Embraer 145. We will start out with a brief system description. Next, we will look at the elevators and the pitch trim system, the roll and yaw control systems, the gust lock and flaps. Finally, we will discuss the spoilers and the stall protection system. We will then conclude this module with a discussion of the various ICAS messages associated with the flight control system. The primary flight control system consists of the elevators, the ailerons, and the rudder. Secondary systems consist of the spoilers and flaps. The elevators provide primary pitch control. The elevators are mechanically actuated by a redundant set of cables, pulleys, bell cranks, and rods. Both control columns are connected by a torque tube located under the cockpit. The torque tube makes the two control columns move together and in sync. The pitch disconnect is located on the port edge of the center pedestal. In the event one of the cable assembly jams, the two sides can be disconnected by means of the elevator disconnection handle. In the event one of the cable circuits jams, pulling on the disconnect handle disconnects the two sides, and the unaffected control column can now control the free elevator. Click on the disconnect handle to disconnect the two sides. Once the disconnect device has been actuated, the elevator disconnect light illuminates. This light is located on the center pedestal. Once disconnected, the control columns can only be reconnected when the aircraft is on the ground. Both the autopilot elevator servo and the stick pusher servo are connected to the left side of the torque tube. Once the elevators have been disconnected, the stick pusher is only available on the left control column. Once the elevators have been disconnected, the autopilot must not be used. Elevator travel is 27 degrees up from neutral and 16.5 degrees down from neutral. Servo and spring tabs located on each elevator help reduce the force required to position the elevators. These tabs are located on the trailing edge of each elevator near the wing root. The servo tab is the outboard one, while the spring tab is the inner one. The servo tab deflects proportionately to the elevator deflection to help elevator movement. The spring tab is used to reduce the control column force at high airspeed. It is connected to the elevator through a torque tube, and it moves in the opposite direction of the elevator movement. The deflection of the spring tab is proportional to the control column force and therefore to the aerodynamic force imposed on the elevator. At low airspeed, the spring tab remains in the neutral position, while at high airspeeds it assists in moving the elevators. An electrically actuated pitch trim system positions the entire horizontal stabilizer surface. It can be commanded either automatically via the autopilot or manually via the trim switches. Pitch trim marks located on the vertical stabilizer provide a visual indication of the stabilizer trim position. The tick marks represent 4 degrees nose down, neutral, and 10 degrees nose up. The nose down position is the top of the scale, while the nose up position is at the bottom of the scale. Each intermediate mark represents a 2-degree change. Pitch trim position is derived from the Horizontal Stabilizer Control Unit, or HSCU. The pitch trim position can be viewed on the ICAS. On the ground, if the pitch trim is out of the green band, the pointer and digital indications will turn amber. The pointer, digital readout, and direction indication are removed from view in the event of a pitch trim miscomparison. Trim switches located on the control wheel and a backup trim switch located on the center pedestal can be used to manually position the horizontal stabilizer and thus trim the aircraft. The horizontal trim is actuated by the trim switch located on each control column and the one located on the center pedestal. When using the main control wheel trim switches or backup trim switch, it is necessary to command both halves together. If only one half is commanded, the control unit will not provide a signal to the actuator. The pitch trim signal is processed by the Horizontal Stabilizer Control Unit, or HSCU. The HSCU consists of two independent and redundant control channels called the main and backup channels. Each channel commands an associated electric motor in the Horizontal Stabilizer Actuator, or HSA. When one motor is commanded to move, the other motor will also be driven via a gear train and coupling, and that motor will follow along even though it is not energized. A 3-second timer prevents a runaway trim situation. When manually actuating the trim will automatically cut out 3 seconds after the trim switches have been actuated. Therefore, you must release the trim switch every 3 seconds and actuate it again in order to continue trimming. The autopilot trim is not limited by this timer and incorporates a separate safety system. To prevent overloading the horizontal stabilizer actuator motor and stalling the pitch trim, it is necessary to trim the aircraft nose down prior to reaching 160 knots after takeoff. Both HSCU channels incorporate a cutout relay that enables the quick disconnection of the respective channel. The cutout relay is controlled by the red Quick Disconnect button located on each control wheel. In the event of a runaway trim, the red disconnect button should be held depressed until a definite disengagement has been accomplished by means of the main and backup system cutout buttons. Click on the red disconnect button to disconnect the pitch trim system. Both HSCU channels incorporate a cutout relay that enables the quick disconnection of the respective channel. The cutout relay is controlled by the red Quick Disconnect button located on each control wheel. In the event of a runaway trim, the red disconnect button should be held depressed until a definite disengagement has been accomplished by means of the main and backup system cutout buttons. Click on the red disconnect button to disconnect the pitch trim system. The HSCU uses data from the air data computers to calculate a trim rate in degrees per second. This trim rate is based on airspeed and changes linearly between 160 and 250 knots. At 160 knots, the trim rate is 0.7 degrees per second. At 250 knots, the trim rate is 0.2 degrees per second. Therefore, the trim rate decreases as airspeed increases. Outside of this airspeed band, the trim rate has two different constant values. The oral warning will sound in the event the trim is not in the takeoff or green range. The trim indicator and associated box and value will turn red when the takeoff configuration is tested or activated by the thrust lever angle. In the event of a failure, the HSCU will send a signal to the Central Maintenance Computer, or CMC. The HSCU will also supply stabilizer trim position for display on the ICAS. Finally, the HSCU sends signals to DAU2 in the event of a channel failure. The stabilizer trim can also be positioned automatically by means of the autopilot. In the event of a runaway, the horizontal stabilizer can be cut off by means of the red guarded switches. The pitch trim is automatically inhibited whenever the stick shaker is activated. We will now look at the roll control system. The aileron systems 1 and 2 shutoff switches are located on the overhead flight controls panel. The aileron disconnect is located on the right edge of the center pedestal. Roll control is provided by mechanical inputs into two hydraulic actuators through independent cable channels. A mechanical reversion enables roll control in the event of a loss of hydraulic pressure. The ailerons can be trimmed to help reduce the required input forces. An artificial feel unit is connected to the right side of the torque tube. Its purpose is to provide an artificial feel of the aerodynamic forces on the aileron. The ailerons are hydraulically actuated by a duplicated system coming from a torque tube under the cockpit floor to the hydraulically powered actuators linked to the aileron surface. The ailerons are driven by dual hydraulic actuators which are controlled by control cables. The control wheels are connected via a torque tube. A disconnect device enables the separation of both sides. The ailerons can be disconnected by means of the aileron disconnect handle located on the center pedestal. To disconnect the ailerons, press the unlock button and pull up on the handle. Click on the aileron disconnect handle to disconnect the ailerons. Once disconnected, the aileron disconnect light located on the center pedestal illuminates, and each control wheel will only control the associated aileron. Once disconnected, the ailerons can only be reconnected on the ground by maintenance personnel. An autopilot servo is connected on the left side of the torque tube. The roll trim servo and the artificial feel unit are connected to the right side of the torque tube. In the event of an aileron disconnect, the artificial feel unit will only have authority on the right side and the autopilot must not be used. Each aileron hydraulic actuator is supplied by both hydraulic systems. The cables from the torque tube bell crank actuate the hydraulic actuators, which in turn position the associated aileron. In the event of a complete loss of hydraulic pressure, the ailerons can still be positioned by means of a mechanical reversion system. The mechanical input from the cables can directly move the ailerons through the unpressurized actuators. The drag of the actuators will result in high control forces, and the Quick Reference Handbook speed restrictions must be adhered to. Each aileron hydraulic supply can be shut off by the associated shutoff switch located on the overhead panel. If an aileron system has been shut off, a caution message will be displayed on the ICAS. In this situation, the ailerons are still hydraulically powered. If both aileron shutoffs are actuated, The ailerons will then operate in the reversionary mode. Roll trim is provided by an electromechanical actuator which is linked to an artificial feel unit. This unit is located on the right side of the torque tube. Roll trimming is accomplished by relocating the neutral position of the aileron. There are no trim tabs associated with the roll trim system. Roll trim is set by means of the dual roll trim switches located on the center pedestal. Both halves of the switch must be moved together in order to actuate the roll trim. Roll trim position is displayed on the ICAS. A 3-second timer provides protection against a runaway roll trim due to a malfunctioning trim switch. Therefore, if the aileron needs to be trimmed more than 3 seconds, the trim switch must be released before the 3-second timer is actuated and actuated again in order to continue trimming. A quick disconnect button installed on the control wheels allows the pilots to disconnect the roll trim while the button is depressed. We will now look at yaw control. The rudder system's 1 and 2 shutoff switches are located on the overhead flight controls panel. Hydraulically powered rudders provide yaw control. The rudders can also be moved mechanically and incorporate a yaw trim system to assist in moving and holding the rudder in the desired position. The rudder is divided into sections that operate in tandem. The forward rudder is driven by the control system, while the aft rudder is linked to the forward rudder and is deflected by the movement of the forward rudder. The trailing edge of both rudders move in the same direction. The rudders can deflect 15 degrees either side of neutral. Control of the rudder is fully duplicated. This consists of cables running from the pedals in the cockpit to the Power Control Unit, or PCU, located in the rear fuselage. The pilot's and co-pilot's control pedals are mechanically interconnected. The position of each rudder pedal can be adjusted forward or aft by actuating an electrical switch just forward of the control column. The pedals are moved forward and aft through a jack screw assembly which provides a travel of 22 inches. The power control unit is powered by both hydraulic systems, and each PCU hydraulic circuit powers one rudder actuator. Therefore, the rudder system is divided into Rudder System 1 and Rudder System 2. The PCU also incorporates an artificial feel device that provides the pedals with an artificial aerodynamic feel of the load imposed on the rudder. An autopilot servo is installed on the left side of the interconnection shaft. The rudder shutoff buttons located on the overhead panel provide a way to manually shut off the associated hydraulic shutoff valve. The automatic shutoff is provided through a speed switch and through the pedals for hard overprotection. The speed switch controls the operation of both rudders. Below 135 knots indicated airspeed, both rudder systems are operating. Above 135 knots, Rudder System 1 is automatically shut off through the rudder electrical circuit. The air data computers supply the airspeed signal. This feature reduces the rudder authority at airspeeds above 135 knots. Rudder System 2 will provide adequate yaw control. In the event Rudder System 2 hydraulic supply fails at airspeeds above 135 knots, Rudder System 1 will automatically resume operation, and a Rudder System 2 inoperative message will be displayed on the ICAS. In the event Rudder System 1 fails below 135 knots, the Rudder System 1 inoperative message will be displayed on the ICAS. If the automatic shutoff fails above 135 knots, both systems will operate the rudder, and a rudder overboost message will be displayed on the ICAS. Rudder System 1 fails in the event of a loss of both ADC systems. A rudder hardover protection system prevents rudder hardover by automatically selecting mechanical reversion mode. A rudder hardover would drive the rudder to maximum deflection and may result in a roll which could be difficult to control. The system consists of spring-loaded cartridges containing a microswitch. This unit detects rudder pedal inputs in excess of 130 pounds. In the event the system detects that the rudder is deflecting in one direction more than 5 degrees while the pilot is pushing on the opposite rudder, the rudder hardover protection system will automatically shut off both rudder systems. The system is operational only when both engines are running above 56% in 2. Rudder authority decreases as the airspeed increases, and at high airspeeds the rudder will not deflect above 5 degrees. Therefore, the rudder hardover protection system will not be activated, as one of the requirements is that the rudder deflects more than 5 degrees plus or minus 1 degree in either direction. Therefore, in the event of a rudder hardover at high airspeeds, the aileron should provide sufficient authority to control the aircraft. In the event of an inadvertent shutoff, the rudder protection system can be reset by pressing both rudder shutoff buttons off, then on. In the event the system has shut down due to a runaway situation, do not reset the rudder systems. An electromechanical actuator provides yaw trim. This actuator is controlled by a yaw trim knob located on the center pedestal. Trimming is accomplished by moving the neutral point. Yaw trim position is displayed on the ICAS. Each tick mark represents 50% of deflection, which represents 7.5 degrees of trim. A 3-second timer prevents a runaway yaw trim due to a failure of the yaw trim switch. In the event you need to trim for more than 3 seconds, the yaw trim knob should be released to neutral after 3 seconds and then actuated again. A quick disconnect button installed on the control wheels allows the pilots to disconnect the yaw trim while the button is depressed. We will now look at the gust lock system. A gust lock system prevents movement of the elevators only. The ailerons and rudder do not require a gust lock, as the associated hydraulic actuators dampen any movement of the surface. The gust lock also prevents the number 1 thrust lever from being moved above the idle position. The number 2 thrust lever may be moved in order to facilitate ground maneuvering. To engage the gust lock system, pull the column to any position from neutral to full nose up. Lift the safety lock device and move the gust lock lever aft to the locked position. Push the control column fully forward until the control column movement is restricted. Locking is now completed. To unlock the controls, lift the safety lock device and move the gust lock lever forward to its intermediate position. The gust lock light on the glare shield panel will illuminate as the locking pins are commanded to open. This will take approximately 10 seconds. After the gust lock light goes off, pull the column backwards to any position from neutral to full nose up. Pull the gust lock lever from the intermediate position to its full forward in-flight position. The unlocking cycle is now complete. Watch this video that discusses the electro gust lock.
The gust lock system used on the Embraer 145 series family has been redesigned to enhance safety and to eliminate the possibility of damage to the elevator surfaces inflicted by strong winds when the aircraft is on the ground. The existing mechanical gust lock actuates on the torque tube which is attached to the control column. This configuration leaves the elevator panels with some undesirable freedom of movement because of the elasticity of the control cables and of the elevator torsion bar. A new electric gust lock system has been introduced to replace the existing mechanical gust lock. The new system acts directly on the elevator panels, preventing them from moving rather than locking the torque tube. Basically, the system is composed of locking pins driven by an electromechanical actuator, which is commanded by the gust lock lever. Locking and unlocking operation is possible on the ground only. Once airborne, the system is de-energized to prevent gust lock lever movement and inadvertent actuation. The system is redundant. No single or even double failure will allow inadvertent locking of the elevator. The new electric gust lock system is easily distinguishable from the mechanical system by the painting scheme and the inscription on the handle. An amber indication light is also incorporated on the glare shield panel to indicate that the electromechanical actuator is moving the pins to unlock the surfaces. This light illuminates only during unlocking procedure. The system is easy to operate, though there are some differences from the old mechanical system. To unlock, lift the handle and move the gust lock lever to its intermediate detented position. The indication light will illuminate and remain on until the locking pins have been fully retracted. Wait until the indication light extinguishes and pull the control column backwards to any position from neutral to full nose up. It will clear the gust lock lever to move further forward of the intermediate stop to its full forward in-flight resting position, completing the unlocking procedure. Remember, gust lock lever command from the intermediate to the unlocked position is not possible prior to pulling the column rearward. To lock the elevator, pull the control column backwards to any position from neutral to full nose up. Lift the handle and move the gust lock lever from the unlocked to the locked position. Push the control column fully forward until the control column movement is restricted. Locking is now complete. In the locked position, one of the thrust levers has some limited travel, enough to provide taxi breakout thrust.
We will now look at the flap system. The flaps on the Embraer 145 consist of two double-slotted Fowler-type flap panels. There are two flaps on each wing. The flaps are electrically operated and they are controlled by a single flap handle located on the center pedestal. The flap system uses electrical power from DC bus 1 and 2. Therefore, you will not be able to operate the flaps in the event of an electrical emergency. The flap selector lever provides 4 detent settings at 0, 9, 22, and 45 degrees of flap. Flap position is displayed on the ICAS. If data is invalid, digits are replaced by amber dashes and a box. In transit, flap position changes to a green dash unless a flap failure occurs, in which case the actual flap position is shown. The control panel on this screen is interactive, so you can operate the flaps. A protection circuit prevents the flaps from moving when the aircraft is powered and a disagreement exists between the flap position and the flap selector lever. To reset the system, lift and release the flap selector lever, and the flaps will move to the position commanded by the flap selector lever. The Flap Electronic Control Unit, or FECU, compares the flap lever position with the actual flap position and commands the Flap Power Drive Unit, or FPDU, to drive the flaps to the selected position. Placing the flap selector lever in one of the detent positions sends a signal to the FECU. Intermediate flap positions cannot be selected due to the absence of flap selector lever signals. FECU outputs consist of flap position, flaps out of 0 degrees, landing flaps 22 or 45 degrees, and flaps out of the takeoff position. FECU protection disengages the FDPU in the event of an incorrect command, incorrect feedback, flap asymmetry, command position disagreement, a disagreement between the feedback, shaft velocity, an inoperative motor brake, and motor arcing. The FPDU consists of 2 electric motors connected to a differential gearbox. Each motor is controlled by the FECU through an independent channel. Both motors drive a set of gears, which in turn drives a flexible shaft. This shaft drives all the flap actuators. 2 flap marks located on each wing's trailing edge indicate flaps 9 and 22. These marks are visible when the flaps move to the respective position. A torque limiting feature prevents the flaps from being overloaded in the event of flap or actuator jamming. 2 transmission brakes and the FDPU motor brake lock the panel when movement stops. Flap asymmetry is detected by velocity sensors located at each end of the flexible shaft. Should this occur, the system is disabled and can only be reset on the ground. Flap limit speeds are 250 knots for 9 degrees of flap, 200 knots for 22 degrees, and 145 knots for 45 degrees of flap. If any thrust lever angle is above 60 degrees and the flaps are not in the appropriate takeoff position while the aircraft is on the ground, the takeoff flaps oral warning message is activated. In addition, the flap position indicator and box displays in red on the ICAS. A similar result is observed if the takeoff configuration button is pressed. At the conclusion of this audio, a takeoff configuration test will be automatically performed with the flaps out of their normal position.
Takeoff flaps.
We will now look at the spoiler system. There are 2 spoiler panels per wing, and they are located just inboard of the flap panels. The spoiler panels provide both speed brakes and ground spoilers. The outboard spoilers are used for both speed brake and ground spoilers. The inboard spoilers are used as ground spoilers only. The spoilers are electrically controlled and hydraulically actuated. A spoiler control unit, or SCU, controls the spoilers. The inboard spoilers are powered by hydraulic system 1 pressure. The outboard spoilers are powered by hydraulic system 2. The outboard spoilers are controlled by the speed brake lever located on the center pedestal. The status of the spoiler panels is indicated on the ICAS. When a spoiler is closed, the caption is a white CLD for closed. When a spoiler is open, the caption is a green OPN for open. The speed brakes are extended by placing the speed brake lever in the open position. This signals the spoiler control unit to command the speed brake valve solenoid to open, which supplies hydraulic pressure from System 2 to pressurize the actuators and deploy the speed brakes. The speed brake panels extend to 30 degrees. The speed brake lever on this screen is interactive, so you can operate the speed brakes. The spoiler control unit will open the speed brake valve solenoid provided the thrust lever angle of both engines are set below 50 degrees, the flaps are at 0 degrees or 9 degrees, and the speed brake lever is in the open position. If the speed brake lever is in the open position, but any of the conditions are not met, a speed brake lever disagree message is displayed on the ICAS. Returning the speed brake lever to the closed position will remove the disagreement message from the ICAS. The disagree message would also appear when the left or right thrust lever is above 50 degrees and the flap position is more than 9 degrees. The ground spoiler system uses all 4 panels. When open, the outboard spoilers extend 30 degrees and the inboard spoilers extend 52 degrees. The ground spoiler system requires power from DC bus number 1 and DC bus number 2. The ground spoiler system will not be available in the event of an electrical emergency. The ground spoiler system is automatic. The spoiler control unit will enable the ground spoilers when all the following conditions are met. The aircraft is on the ground, the main landing gear wheels are running above 25 knots, and the thrust lever angle of both engines are set below 30 degrees, or N2 is below 56%. If any thrust lever angle is above 60 degrees, and any spoiler or speed brake panel is deployed, the takeoff spoiler's oral warning is activated. In addition, the spoiler open label displays in red on the ICAS. A similar result is observed if the takeoff configuration button is pressed. At the conclusion of this audio, a takeoff configuration test will be performed with the speed brake panels deployed.
Takeoff spoilers.
We will now look at the Stall Protection System, or SPS. The Stall Protection System is designed to detect and avoid stalls. The Stall Protection System consists of a stall computer with 2 independent channels, 2 angle of attack sensors, 2 stick shaker actuators, and 1 pusher actuator. Each SPS channel receives information from the attitude and heading reference system, the air data computers, the flaps, the spoilers, the landing gear, the air ground switch, the wind shear detection system, and the radio altimeter. Using inputs from various sources prevents spurious system activation. The stall protection set point varies depending on the position of the flaps, landing gear, Mach number, and wind shear conditions. In addition, the stall protection system will actuate at reduced angle of attack values for flaps 9 and 22 in the event the ice compensation system is active. Each SPS channel receives information from its associated AOA sensor and supplies it to the opposite channel. This compensates the reading for any side slips. A locked AOA sensor is not considered in determining the onset of a stall. In the event the system senses a stall, the stick shaker actuates and the autopilot disengages. If no corrective action is taken, the stick pusher engages and commands the aircraft nose down. The aural warning unit generates a clacker sound. The pusher is inhibited when the aircraft reaches 0.5 Gs to avoid any negative G loads. The pusher will not activate if the aircraft is on the ground except during a test, the quick disconnect button is pressed, either cutout button is pushed, below 200 feet radial altitude, below 0.5 G, above 200 knots. One subsystem is inoperative since both channels need to be operating in order to command a stick push. The stall protection system is controlled by the SPS panel located on the center pedestal. It has 3 buttons: Test, Cutout 1, and Cutout 2. The Test button is used only on the ground. When the Test button is pressed, a self-test sequence is started and the following occurs. The button illuminates amber, both shakers activate, the pusher activates, the button extinguishes within 5 seconds. Pushing the test button in flight will activate the stick shaker, but not stick pusher. You should note that the control column must be held full aft while conducting the test in order to prevent the columns from slamming forward. The control panel on this screen is interactive, so you can test the stall protection system. For this simulation, the aircraft is on the ground. SPS System 1 is powered by DC Essential Bus 1. SPS System 2 is powered by DC Bus 2. In the event of an electrical emergency, the stick pusher and stick shaker number 2 will be inoperative. However, stick shaker 1 will still operate. We will now look at the various ICAS messages associated with the flight control system. The pitch trim 1 or 2 inoperative message indicates that the associated pitch trim system is inoperative. Some aircraft have a pitch trim main inoperative warning message that indicates that the main pitch trim system is inoperative. The message is also displayed if the quick disconnect button is held pressed for more than 11 seconds. The main trim switches are actuated when the horizontal stabilizer actuator is stalled, or the main trim switches are actuated when the backup switch is driving the pitch trim. These aircraft also have a pitch trim backup inoperative warning message that is displayed for similar conditions. The aileron system 1 or 2 inoperative message indicates that hydraulic actuation of the associated aileron system is inoperative. The rudder system 1 inoperative message indicates that the rudder system 1 is inoperative when the airspeed is below 135 knots indicated airspeed. The message is also displayed at speeds above 135 knots if the airspeed data from both ADCs is invalid. A rudder system 2 inoperative message indicates that rudder system 2 is inoperative. In the event both rudder systems are inoperative, the ICAS will display a rudder system 1-2 inoperative message. A rudder overboost message indicates that both rudder systems' hydraulic actuators are pressurized with the airspeed above 135 knots. The rudder HDOV protection failure message indicates a disagreement between both FADECs on the same engine, or that the rudder position microswitches indicate that the rudder is to the right and left simultaneously. A flap failure caution message indicates that both flap channels are inoperative. A spoiler failure message indicates that any spoiler panel is inadvertently opened, failed to open, or if there is any failure in the input signals. A speed brake lever disagree caution message indicates that the speed brake lever is in the open position, but the speed brake opening logic is not satisfied. A flap low speed advisory message indicates that one flap channel is inoperative. This concludes the flight controls module.